Welcome back. So, last time, I think we were talking about C-sortable elements. So recall we have a finite irreducible Coxeter group W, and we're going to fix a standard Coxeter element C. And then remember we had a way of defining these C-sortable elements, so we said you write out C to the infinity, so you just write out C, C, C a bunch of times. And then if you have this element W, you can look for the lexicographically first subword of C to the infinity that is a reduced word for W. This is the C sorting word for W. And then we said you can define like ICK to be the set of simple reflections that you get from the kth copy of C. And if you have this chain of inclusions where IC1 contains IC2, contains IC3, and so on, then we say that W is C-sortable. So remember we said we can let Kame sub C be the set of C-sortable elements of W, and we view this as a subposet of the weak order, the right weak order. Then I was stating this theorem, which maybe I'll write again due to reading. So first of all, Kame sub C is actually a sublattice of the weak order. And for each W and W, if we look at the set of C-sortable elements that are less than or equal to W in the weak order, this has a unique maximal element. So the set of, well, I guess I can write it as set of Y in Kame sub C, such that Y is less than or equal to W, has a unique maximal element that we'll call pi C down of W. So the pi down is like it's projecting down to the Cambrian, so this will be called the Cambrian lattice. So pi C down is projecting down to the C Cambrian lattice. And this map, pi C down, goes from W to Kame sub C. This is a surjective lattice homomorphism. From, or maybe I should say, from the weak order to Kame sub C. So maybe I should mention that when you have two lattices L and L prime, if you can find a surjective lattice homomorphism, so what is a lattice homomorphism? It's just a map that preserves the mean and the join operation. So if you think of a lattice as an algebraic object where the operations are mean and join, then homomorphism means what you think it should mean. And when you have a surjective lattice homomorphism from a lattice L to a lattice L prime, you say that L prime is a lattice quotient of L. And this is just like in the case of, say, group theory. If you have a surjective group homomorphism, then the image is a group, it's a quotient group of the original group that you started with. Similarly for like rings or whatever other algebraic objects. So in this case, we can say that the Cambrian lattice is a quotient of the weak order, but it's also a sublattice, and these are not the same things. You can, in general, have a sublattice that is not a quotient, and you can have a quotient that is not a sublattice. Or wait, yeah. But in this case, it's both. Right. So maybe I'll just say this is called, so Cam sub C is the C Cambrian lattice. So here's a fact. So when W is the symmetric group Sn, if you take the Hasse diagram of Cam sub C, this is isomorphic as a graph to the one skeleton of a certain polytope. So of an n-1 dimensional polytope. And this polytope is famous, and it's called the associahedron. And by one skeleton, what I mean is you draw your polytope, and you say, I'm going to form a graph where the vertices are the vertices of my polytope. And if there's an edge of my polytope connecting two vertices, then that becomes an edge in my graph. So let me show an example. Actually, first let me define an equivalence relation. So define an equivalence relation on the Coxeter group W by, or I'll say as follows. We'll just say that U is equivalent to V if and only if pi C down of U equals pi C down of V. In other words, the equivalence classes are just the fibers of this lattice homomorphism pi C down. So let me draw an example. So remember I had this picture that I drew before in the case of W is S3, and I'll take C, let's say, to be S1, S2. Doesn't really matter, I guess. And I had this picture where I drew the braid arrangement. It looks something like this. So really, the braid arrangement lives in a three-dimensional space where you think of these as like coming out of the blackboard, but it's nice to draw it in this two-dimensional picture. Well, I guess you could also define things so that it's in a two-dimensional space. This is fine. Then we can draw the like we can identify the regions of this arrangement with the elements of S3. So we have the identity at the bottom. Here's S1 and S2. And this will be S2, S1. And this will be S1, S2. This will be S1, S2, S1, which is also S2, S1, S2. Now I can draw the what's called the permutahedron, which is basically the weak order, like as a graph. So this is some polytope. In this case, it's a hexagon. So I guess really the permutahedron is this hexagon, but like including like the interior. But the one skeleton of this polytope is just the graph out here. It's just the vertices and the edges sort of ignoring the interior. So in this case, the one skeleton of the permutahedron as a graph is isomorphic to the Hasse diagram of the weak order. In this case, I think I drew the right weak order. And it turns out you can do something similar with the associahedron, so I'll show you how that works. So let's look at what pi down is doing. Maybe I'll use yellow for this pi c down. So in this case, the only element that is not C sortable is S2, S1. So this is because, well, remember what it means to be C sortable. You write out the C sorting word and you look at the inclusions of these sets. In the case of the identity, you just have a bunch of empty sets, so that's very easy to see that it's C sortable. For S1, you just write down an S1, and that's like one set. So, right, this would be saying, like, the fact that this is C sortable is saying, like, the set S1 contains the empty set, and so on. And similarly for S2, if I did S1, S2, then what I write down to begin, like my IC1 would just be S1 and S2, and then I get a bunch of empty sets. If I wanted to do this with S1, S2, S1, I would get S1, S2 as my first set, and then I would get S1, and then I would get a bunch of empty sets. So the only one that ends up not being C sortable is this element here. So when I do pi down is projecting down to like the biggest C sortable thing that is below me. So for all of these elements that are C sortable, it's just going to fix them. So let me use yellow for pi C down. It's just going to fix this element. It'll fix this element, fix this element, fix this element, fix this element. And for this one, it's just going to send it down here. Okay. So let me draw this picture again, but I'm going to glue. Yeah, so maybe what I'll say is in Sn, let's glue equivalent regions of the braid arrangement. And by equivalent, I mean this equivalence relation that I've defined as the fibers of pi down. So let me draw this picture again. But now I'm going to glue these two regions together because they're in the same equivalence class. So I have this picture now. And so now, right, so I've sort of like, I guess, glued this region here. And the polytope that I get, you can kind of imagine what's happened is I've taken my permutahedron, my hexagon here, and I've kind of, so I still have this part. And I've kind of removed this facet here, this edge. And if I remove that, it's kind of like these lines continue out like this. And so now you end up with a pentagon which is actually the two-dimensional icosahedron. And in general, this will work for higher dimensions as well. So here I'm just doing this in the case of S3, but you can do this in higher dimensions. And by gluing these regions together, you'll end up going from the permutahedron to the icosahedron. And one of the things that's cool about this is that, again, this doesn't, well, the polytope that you get doesn't depend on the choice of C. For any choice of C, the polytope you get will still be the icosahedron. So like any two choices of C will give you isomorphic polytopes, but the lattices that you get, the Cambrian lattices, are actually different. You won't see that, I guess, in S3, because there are only two Coxeter elements, or two standard Coxeter elements, and they will give you isomorphic Cambrian lattices. But if I did this in, say, S4, then I could find non-isomorphic Cambrian lattices. Okay? So one of the motivations for doing this.
Sorry, can you say that again?
Yes. So if you choose different C, in general, you will get different Cambrian lattices. Like the lattice structure of Cam sub C, they will be different. But the polytope that you get, any two of them will give you isomorphic polytopes, namely the icosahedron. Or another thing I could say is that like the Hasse diagrams will be isomorphic as graphs. So this is kind of weird. It's like you choose two different C's, you get these different lattices, but like as graphs, the Hasse diagrams are isomorphic. And it's kind of like what you're doing is you're taking the icosahedron and you're like orienting the edges in different ways. And for different orientations, you get different poset structures, but the underlying graph is always the same.
So, sorry, I guess which properties are invariant about C in the choice of C?
Right, so, well, anything that depends on the polytope, or in particular the graph. So if you're thinking of it as a lattice, like, okay, the number of elements, it's going to be the Catalan number. The number of edges in the Hasse diagram will be the same, but I think a lot of other properties will be different. I mean, do you have any things in mind, like properties in mind, that you would want to be invariant?
So I guess like they're not like conjugates of each other.
Right. Well, I mean, yeah, I guess I don't know what conjugate would mean, but right, they'll behave differently. Yeah, in some sense. I guess I didn't prepare an example in S. Well, maybe I could pull up an example. Oh, but I don't have my phone because it's recording. Okay. Well, anyway, you can believe me that they are different. Yeah, in general. Okay. So there's one special Cambrian lattice which kind of motivated a lot of this story, and this is called the Tamari lattice. So when, maybe I can put this here. When W is the symmetric group Sn, and C is this special, sometimes this is called the linear Coxeter element. It's just S1, S2, ... Sn minus 1. In this case, remember in this case that the C-sortable elements are just, so Cam sub C is the set of 3, 1, 2 avoiding permutations in Sn. And in this case, Cam sub C is something called the nth Tamari lattice. And this was introduced by which was introduced by Dov Tamari. In 1962. And Tamari lattices have been studied a lot. So there are tons of papers written about just properties of Tamari lattices, because they're kind of at a good level where they're like, you can say interesting things about them, but it's not like trivial. So you have to work to prove things, but like you can say interesting, nice things about them. So anyway, these are the Tamari lattices in this special case. Basically, it's just take the 3-1-2 avoiding permutations under the weak order. Although this isn't how Tamari originally defined it. I think Tamari was looking at like bracketings, like certain parenthesizations of words, and there's a way of defining and ordering on that. But there are a bunch of objects that are counted by the Catalan numbers, like the 3-1-2 avoiding permutations, and there are various different ways of defining the Tamari lattice on different combinatorial objects. But the way that I like to do it is just take the 3-1-2 avoiding permutations under the weak order. Any questions up to here? Okay, I'm going to go back and talk more about pop stack sorting. So I brought the last box of Rice Krispies, if anyone wants the Rice Krispies. I don't want it, but okay.
I'm sorry.
Yes.
What is it? When you say can the TI and then the bipartite,
Yeah, okay, so that's a good point. Actually, maybe I should mention that before let me mention that. Because we've been talking about Coxeter elements. So here, this is one special Coxeter element called the linear Coxeter element. And there's another special one, which is where you write down the simple reflections that have odd indices, and then you write down the ones that have even indices. So, actually, okay, you can do this with odd and then even, or you can do even and odd. So the bipartite Coxeter elements are, well, I could do S1, S3, S5, and so on, writing down all the ones with odd indices, and then the ones with evens. Or the other one is, if I just switch these. And it turns out that these Coxeter elements are also nice in some ways, just like how the linear Coxeter element is nice. One of the cool things about the bipartite Coxeter elements is that you can define these in a natural way for other finite irreducible Coxeter groups. Because, okay, so like what are you doing with the linear one? You're basically saying write down the Coxeter graph of Sn, which is a path graph. And you say, I'm going to go from one side to the other, just reading along the path. This doesn't really make sense if you write down the Coxeter graph of something like Bn, because it's got like a fork. And so it doesn't really make sense to say like go from one end to the other. But there is a notion of bipartite because any finite irreducible Coxeter group has a Coxeter graph which is a tree. And the reason it's called bipartite is so, okay, more generally, if W is finite and irreducible, then its Coxeter graph is a tree. In particular, it's bipartite, just meaning that I can split up the vertices into two sets so I can say find a bipartition of the Coxeter graph, which I'll say is X disjoint union Y. And this just means that none of the vertices in X are adjacent to each other and none of the vertices in Y are adjacent to each other. And then you can say, let's let C sub x be the product of the simple reflections in X. I'll do an example in a second. So this is the product over S in X of S. And let C sub Y be the product over S in Y of S. Then if I take Cx, Cy, or I could take Cy, Cx, these are bipartite Coxeter elements. So like as an example, if I wrote down, I don't know, like D6. So this is D6. And if I want to do my bipartition, I get two colors. I could say, okay, maybe this is one set, and this is the other set. And basically all I'm saying is I write down the product of the green simple reflections, right? So each vertex corresponds to a simple reflection. So I write down the product of the green simple reflections and then the product of the orange ones. And one thing I should point out is that it doesn't matter the order that I write down the green ones because they all commute with each other because none of them are adjacent to each other. So if I wrote like this green, this green, this green, this green, that's the same as if I did like this times this times this times this. It doesn't matter the order. Similarly for the orange ones. So really you just get these two bipartite Coxeter elements. Yes?
So for some choices of C, the lattices are isomorphic, right?
For some choices, yeah, they'll be isomorphic.
So is it note how many there are?
Oh, how many different isomorphism classes? I don't know off the top of my head. I mean, so what I'm thinking is that there are sort of easy examples where you can get isomorphisms, like if you apply an isomorphism of the Coxeter graph. Like, for example, if I did in type A, I could just do Sn minus 1, Sn minus 2, dot, 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 S3, S2, S1. And I mean, that's going to give me something isomorphic because it's sort of like the same in some way. It's just going the other way across the path. But in general, I don't know what the different thing, yeah. Any other questions? Okay, so here, I thought I would mention this just because it's a paper that I'm currently writing, although hopefully it'll be done in the next month. But this is just, I think it fits in nicely. So this is a theorem with Emily Barnard, myself, and Eric Hansen. I guess I'll write 2023 plus plus, and the plus plus means that it's not yet on archive, but it will be hopefully soon. So this is going back to POP, but we're going to do POP on an arbitrary Cambrian lattice of an arbitrary finite irreducible Coxeter group, and we show that the maximum number of iterations of POP needed to send an element of the Cambrian lattice Cam sub C. So here Cam sub C is any Cambrian lattice of any finite irreducible Coxeter group to the bottom element zero hat is H minus 1, where remember H is the Coxeter number of W. And I'll remind you this is 2 times the number of reflections over the number of simple reflections. So this is the Coxeter number. Of W. So I think I mentioned before that in the case of, like if you look at the weak order on Sn, this was proven by, well, that's not this, but like in the case of the weak order on Sn, Unger proved that the maximum number of iterations of pop needed to go to the bottom is n-1, which is the Coxeter number -1 in the case of the weak order. And then I proved that this is also true for the weak order on any finite Coxeter group, but it turns out it's also true if you take the weak order, or if you take any Cambrian lattice, you still get the Coxeter number -1 showing up.
It actually achieves the bound.
Yeah, right. So that, I think, was the trickier thing, trying to construct an example that actually attains the bound.
Is it the same paper as?
This is also the same paper. Yeah, I'll mention that. Okay, I'll mention more pop stack sorting stuff. So this is a theorem that was proven by one of my REU students. This is Karina Hong, I guess published in 2022. So here, we're going to so it turns out that the Tamari lattices interact really well with pop. And one of the nice things here is that like you can say very precise things about pop on the Tamari lattice, but it's like the right level where it's difficult, but it's like within reach, and you can say something very clean. So let A sub t of n be the number of elements of the nth Tamari lattice that require t or fewer iterations of pop to reach bottom. So in other words, they're the elements such that if I start at that element and I apply pop iteratively t times, then I get to the bottom. So I guess I haven't talked about generating functions, but I will at some point. And the point is that if you have a sequence of numbers like this, then you can encode them with a power series called a generating function. So this might look something like this. So I'm going to fix t and look at the sum over n greater than or equal to 1 of a sub t of n z to the n. So for a fixed t, like t equals 5 or something, this is encoding all of these numbers. And in this case, there's like a nice simple expression for the generating function. And so I guess one of the nice things about generating functions is sometimes the expression that you get at the end is very simple, and so it's nice that you can write it down in a simple form. In this case, it's z divided by 1 minus 2z minus the sum from j equals 2t of, this is the j minus first Catalan number. I guess earlier I was calling it cat of Sn, but here I'll just, okay, this is the j minus first Catalan number, z to the j. So like if t is 4, this would be z over 1 minus 2z minus z squared minus 2z cubed minus 5z to the 4th.
what other lattices is that known?
Good question. I mean, I think it's only really been, like, this level of precision has only really been written down for the Tamari lattice. I think probably for some distributive lattices you could write down something precise. I don't know how to do this for other Cambrian lattices though.
Just asking that.
We sorry?
Just asking.
Oh, also, yeah, for SN, oh, that's a good point. So there was, yeah, just for SN, there was work on this that was like before I came along. And, okay, so for t equals 1, so if you want to know the number of elements of SN that go right to the bottom, there are 2 to the n minus 1 of these, and they turn out to be the long elements of parabolic subgroups. So the point is that a parabolic subgroup is determined by choosing a subset of the n minus 1 simple reflections, and there are 2 to the n minus 1 ways to do that. For each one, you get a long element of that parabolic subgroup, and those are the elements that get sent right to the bottom. For t equals 2, there's a paper by Pudwell and Smith where they write down some generating function. Like the whole point of the paper is just for t equals 2 to figure out what it is. I don't remember what it is off the top of my head. And then for higher values, there's a paper by Clausen and Goodmanson where they write it, I think they do write it down for t equals 3, but it gets very complicated for higher values of t. And what they show is that for any fixed t, the generating function that you get is a rational function. So like in the sense that it's a product of polynomials. So like if you took t equals 20 and you said form this generating function except you're replacing the Tamari lattice by the weak order on S20, it would be some god awful like rational function, but like I don't know how. I mean, you could. I think they give an algorithm for maybe for computing it or something, but it's some awful thing.
Oh, so it's nicer for the Tamari.
It's way nicer for the Tamari lattice, yeah. Yeah.
Question.
Yes.
Is that thing you said about long elements of parabolic subgroups through every finite irreducible Coxeter?
Yes.
Okay.
Yeah. For any finite irreducible Coxeter group, the elements that get sent immediately to the bottom are just the long elements of the parabolic subgroup.
So it's always 2 to the n minus.
That's all. Yeah. So that's always going to be a power of 2. Yeah.
2
Good point.
n.
Right. Yeah. 2 to the number of simple reflections. Okay. Any other questions?
Just to make sure that's the J minus first category number.
Yes. Okay, so let me tell you about another, I'm supposed to be doing combinatorics in this class, so let's do some other classical combinatorial objects.
Oh, sorry, one last.
Yeah.
That's not known for Cambrian bipartite.
Right,
Okay.
right. It's not known for Cambrian bipartite. In fact, we do not know the number, so okay, I think there are 2 bipartite Coxeter elements. Let me focus on this one, because I think they actually end up being different if n is, like, depending on the parity of n. But let me just focus on the one where it's odds first and then evens. I think we conjecture that, like, you can look at the number of elements that require n minus 1 iterations to get to the bottom. So this would be like the biggest number in the sequence. I think we conjecture that this is either 1 or 2 depending on the parity of n, but we don't know this. So like even that for the bipartite Coxeter element, we don't know. And so we definitely don't know like this even more refined result of like the entire enumeration of how many elements require t iterations. Yeah. Okay. So a Dick path is a lattice path using unit up steps and unit down steps. that, so it's in the plane, it's going to start at the origin. Well, maybe I'll say it starts at, the origin. It ends somewhere on the x-axis. I'll draw pictures, so maybe that'll help make this clear. Ends on the x-axis, and it never passes below the x-axis. Okay, let me draw a picture. So maybe here's my So I'm going to draw a lattice path that starts here, which will be the origin. And at each step, I can either go basically one step northeast, so that'll be a unit up step, or I can go one step southeast, and that'll be a unit down step. So for example, I could go northeast, and maybe northeast again, and then maybe southeast, and maybe I'll go up, and then up, down, down, up, down, something like this. And maybe that's my dick path. So I go up, up, down, 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 up, down, 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 up, down. I guess another way of thinking about this is if you just think of this as a sequence of ups and downs, then I just want some sequence of ups and downs so that the total number of ups is equal to the number of downs. That's the condition that I end on the x-axis. And the condition that I never go below the x-axis says that for any prefix of my sequence, the number of ups should be greater than or equal to the number of downs. Okay? So these are very classical combinatorial objects, and they're counted by the Catalan numbers. So the number of dict paths of length 2n, and by length 2n I mean it has in up steps and in down steps. This is, so I guess I've switched over to using C sub n for the nth Catalan number, so it's C sub n. This is what I was calling cat of Sn before. And we can define a partial order on dict paths, which I think I mentioned this in the P set. So let me go over here. So let's define a partial order on the set of dict paths of length 2n so that if I have some dict path lambda, then I'll say this is less than or equal to a dict path lambda prime if lambda lies weakly below lambda prime. So it's sort of like one of the most natural partial orders that you could put on these. And I'll show you what this looks like for n equals 3. So the bottom dig path will just look like this, where I go up, down, up, down, up, down. And then over here, I'll have the dig path where I go up, down, up, up, down, down. And this one is less than this one, because if I sort of imagine superimposing these, like if I put this dig path over here, you would see that this one lies weakly below this one. Like if I sort of drew up, down, up, down, up, down, it's below that one. And then similarly, I could draw up, up, down, down, up, down. This also lies above this one. Here I'll do up, up, down, up, down, down. Oh, I didn't leave myself very much room. Let me make this smaller. Up, up, down, up, down, down. And then finally at the top, there's just up, 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 down, down, down. Okay? So you can see there are 5 of them, because 5 is the third Catalan number, and they have this partial order. So on the P set, I asked you to show that this is a distributive lattice for any n. Although maybe at some point I will end up saying something that just gives this away pretty easily. I don't know. But anyway, whatever. Okay, so these are dig paths. There's another kind of lattice path that's nice. These are called Motzkin paths. So I guess I'll write this out, but the examples make it easier to understand. Okay, so Motzkin path is a lattice path. Using unit up, unit down, and unit horizontal steps. That starts. Well, okay, it has basically the same properties as dig paths, except you're allowed to use these horizontal steps. So I want to start at the origin. Starts at the origin. Ends on the x-axis. Never passes below the x-axis. So I'll draw examples of these. Let's say n equals 4. Or, okay, I guess I haven't defined n. I'll just draw the Motzkin paths of length 4. So there's horizontal, horizontal, horizontal. So I just use 3 horizontal steps like this. Oh wait, no, I want 4 actually, sorry. 4 horizontal steps. Or I could do horizontal, horizontal, up, down. Or I could do horizontal, up, down, horizontal. Or I could do horizontal, up, horizontal, down. Or I could do up, down, horizontal, horizontal. Or up, horizontal, down, horizontal. Like that. I could also just do up, up, down, down. Or I could do up, down, down. So these 2 are actually just dig paths, but that's fine. And then there's one more, which is up, horizontal, horizontal, down. So the number of Motzkin paths of length n is called the nth Motzkin number. And so this shows that the 4th Motzkin number is none. So the 4th Motzkin number is 9. So here is a theorem. So one thing you can do, again with pop, is you can look at the image of pop. So if I did pop on this lattice, let me use a different color, then I would say, so this element gets sent here. So I take the meat, this covers only one thing, so I take the meat of that thing, which is just that thing. If I take pop of this, I take the meat of the 2 things that it covers, which is the bottom. Pop of this element would be the bottom, pop of this is the bottom, and the bottom is fixed. So the image of pop in this case is this element here, and this element here. And so there's the theorem which came way before I called this pop, although it was phrased in a different way, and then I found that it's equivalent. But there was a paper looking at the image of pop on this lattice of dig paths. So this is due to Sapanakis Tassalas and Sicarus. This is in 2006. Okay, this is probably the only time that this theorem will be mentioned in a class anywhere. So the size of the image of pop. So again, they weren't calling it pop, they had some other name for it. But on the lattice of dict paths, of size 2n, or of length 2n, is, okay, so they show that it's the sum from k equals 0 to n minus 1 of 1 over k plus 1, 2k choose k, n plus k minus 1 choose 3k. Some formula. And I will mention that this was refined recently by Yunso and also Nathan Sun. They were also my RU students. So by Choi and Sun recently. So I guess the point is you can say, you can count the number of elements of the image according to like the number of edges that the element has going up. So here this element has one thing going up, this element has two things going up. So you could write down a generating function where you have a variable q that keeps track of these things. So I would say this would contribute a q because it has one thing going up. This has q squared because it has two things going up. So my generating function here would be q plus q squared. And so the point is if I set q equals 1, I get 2. And that's counting these two elements. But in general, you can get a formula, and this is what Yunso and Nathan did, finding a formula for what this generating function is with the q's. Okay. Oh, maybe I'll also mention that, because we were talking about the weak order earlier. So, okay, you can also look at the image of pop on other lattices. You can start with the weak order, for example. And there's a paper by Claassen, Gudmundsson, and Pantone where they find a polynomial time algorithm for computing the size of the image of pop on a on the weak order. Actually, let me mention something about this because it's relevant to one of the homework problems. Maybe this is like a hint for, I think, problem 1. So I guess the point is that the image of pop on the weak order is actually hard to understand. So the whole point of their paper was not, like they don't even get an exact formula like this for like the number of elements. They just say like we have an algorithm for computing these numbers. It's like a polynomial time algorithm. But I'll just mention, so this is like a hint for one of the p-set problems. Every permutation in the image of pop on Sn, on the weak order on Sn. So like this is the original pop stack sorting thing where you reverse the descending runs. Has all of its descending runs of size at most 3. So actually, okay, I should say you should prove this if you're going to use it on the p-set. So prove this if you want to use it. I think there is a way to do this p-set problem. I think it's like 1b. There is a way to do it not using this, but I think that's a little trickier to find. But there is a way to do it using this fact.
It's still hard.
Okay, it's still hard after that.
I agree.
Okay, okay. Should I give a hint?
Yeah.
Another hint? Okay, so if I have a, okay, so I'll remind you what the problem says. So the problem was to show so this is p set 3, problem 1b. Show that, I think I was calling it script p in. So this is the average number of iterations of pop needed to sort a random permutation. Show that this is at least 1/2 n minus little o of n. And what I'll say is that if I have a random permutation, so imagine I plot my random permutation. So I'm going to plot it, and what it's going to look like is this. Okay. It's going to look like this. Right? So that's the random permutation. And the point is that with very high probability, there will be numbers, or there will be points down in a little box down there. So in other words, if you choose a random permutation, then with high probability there will be relatively small numbers relatively close to the end of the permutation. And what you can do is try to look at what happens to these numbers as you apply pop. So the first iteration of pop is going to do something, but after you do one iteration of pop, like once you apply pop once, now you're in the image of pop, and all of the descending runs have size at most 3. And so when you reverse descending runs, if each one has size at most 3, this gives you control over like how far these points, how far these numbers can actually move. And the point is, if you're going to sort something, the numbers that are small have to make it all the way to the left. So if they start,
Sorry.
Yep.
So it's really hard to analyze whether that descending run is size 32, right? Or length 32.
wait, sorry, analyze whether what?
That
Oh.
descending run that contains that small number is size 32.
Yeah, right.
Okay, so there's nothing in your pop.
Right, I mean, ideally it would be nice to say that like it's usually 2, because that would allow you to show that it actually takes close to n steps to get to the end.
Yeah.
That would help resolve this conjecture that I have, but I don't know how to do that. So this is what I know how to do. Okay. So let me mention another theorem that Karina proved. This is about the image of, so again, the Tamari lattice is really nice. This is about the image of pop on the Tamari lattice. So the size of the image of pop on the nth Tamari lattice is the n minus first Motzkin number. So I'll give an example of this. So let's say here S3, the weak order on S3 looks like this. We did this. So here's 3, 2, 1. Here's 2, 3, 1. 2, 1, 3. 1, 2, 3. 1, 3, 2. 3, 1, 2. So if I look at the Tamari lattice, these will be the 3, 1, 2 avoiding permutations, which are these. So I get this picture. Let me call this tam sub 3. Tam sub 3. So this is the third Tamari lattice. It's just these 5 elements under the weak order, so it looks like this. And if I do pop, so the top element goes to the bottom element is fixed, these 2 elements go to the bottom, this element goes down here, and so these 2 are in the image, so we get 2, and this corresponds to 2 Motzkin paths of length 2, which are these 2. Maybe in the last few minutes, we'll mention another result now about the type B Tamari lattice. This is also Muso's with Nathan. So I guess I haven't defined the type B Tamari lattice, but one way you can do this is you can say, well, the Tamari lattice is defined by saying, well, the Coxeter graph of Sn is a path, and you choose the Coxeter element where you just go down the path from left to right. Well, the Coxeter graph of Bn is also a path, except there's like this one edge labeled by a 4, but that's okay. You can still go down the path from left to right. So the type B Tamari lattice I guess I'll call tam of B in, is, well, it's this Cambrian lattice Cam sub C, where C is the Coxeter element S0, S1, Sn minus 1 of the hyperoctahedral group Bn. And so the theorem that Muso and Nathan's son prove is about the size of the image of pop on tam of Bn. So the size of the image of pop on tam of Bn is the sum from k equals 0 to the floor of n plus 1 over 2. N minus 1 choose k. N plus 1 minus k choose k. Are there any other questions? I have one other thing that I'll say about pop, and then I think next time I'll start talking about the geometric way of thinking about Coxeter groups in terms of like hyperplanes and root systems and that kind of stuff. But I don't want to start that right now. So, well, let's see. Yeah, I'll say one more thing next time and then I'll go on to that. Any questions? I guess we can end a little early.